Everyone, I'm Ajitari Nada, a junior at Nueva High School. Throughout this project, I hope to unravel the unknown mechanism of macrolides using structure-based drug design that will help address the mucus hypersecretion and inflammatory respiratory diseases. Having experienced asthma most of my life, I understand the impact of excess mucus on quality of life, especially for athletes like myself. This is what prompted me to explore the effect of macrolides on inflammatory respiratory diseases like COPD, asthma, and IPF. More importantly, inflammatory respiratory diseases, IRD, like COPD, asthma, and IPF, are on the rise with the increase in air pollution, impacting both quality of life and morbidity rates. According to NIH data, there are 65 million people worldwide and 16 million Americans impacted by COPD, which is the fourth leading cause of deaths in the US. Also, as of 2017, there are 1.5 million ER visits and 182,000 inpatient stays resulting from asthma. So this is an important problem to solve. The other key point to note is that there is an opportunity to design a drug that primarily targets mucus hypersecretion while minimizing the antibiotic side effects or risk of resistance. This background motivated me to explore this area more deeply. Let's take a quick look at what an inflamed respiratory tract looks like. As you can see, there is swollen lining and excess mucus blocking the airways. It is important to note that there are currently no approved on-label medications that directly address this arm of the disease pathology. Macrolides are a class of antibiotics that usually target bacterial infections, like erythromycin, azithromycin, and amoxicillin. There are many published studies on the anti-inflammatory therapeutic side effects of macrolides, which are separate from their primary antibiotic effect, based on binding the bacterial ribosome. Macrolides create a distinct anti-inflammatory effect by reducing cytokines like IL-8 and TNF-alpha. They also have a potent mucus-reducing effect by reducing mucus expression like MUC5AC and MUC2. Therefore, my hypothesis is that there must be one or more human macromolecular binding targets for these anti-inflammatory macrolides, and this binding target is still unknown to this day. This project included two key steps to be followed by a wet lab post-pandemic. The first aim of this study is to generate biologically relevant 3D structures of macrolides and identify flexibility sites through all atom molecular dynamics. As you can see on the macrolide panel derived from MD simulations, there are clear differences in flexibility and structure across active, inactive, and control macrolides. You can also see an example of a 1 nanosecond of azithromycin solvated in water, or if the flexibility of the compound is exhibited during the simulation process using the charm force field. The second aim of this study, after the energy minimized 3D structures are generated, is to reverse screen these macrolides against 17,000 macromolecules in the SCPDB database. This will help us find the best target for the macromolecule based on the binding energy. SCPDB is an annotated archive of druggable binding sites extracted from the protein data bank. Inverse screening means that instead of the usual testing of a library of drugs against one target, I will test each macrolide against our library of candidate target proteins. Let us take a look at the Advena screen here that shows the process of converting a 2D structure into a 3D structure, which will be used to prepare ligands for inverse docking. The 2D structure of lecithromycin, drawn in Marvin's sketch, is first saved into PDBQT file format. Through Autodoc Vena tools, the ligand is then input and we get the 3D converted structure for this inverse docking. Screening was also done for the created protein database, with more recent macrolides which potentially address mucus hypersecretion. These recent macrolides identified from literature are enhanced versions of the known macrolides like azithromycin, erythromycin, and clarithromycin. Comparative analysis was then executed of the known and well-studied macrolides and the more recent macrolides like lecithromycin to identify the top 10 targets that effectively address mucus hypersecretion and inflammatory respiratory diseases. This comparison of macrolides with respect to binding energy scores, pocket properties, structural aspects of the macrolides also resulted in newly optimized structural binding relationships. In terms of future steps, the shortlisted protein macrolide complexes will be subjected to further molecular dynamic simulations to validate the selected 10 targets that effectively address mucus hypersecretion and inflammatory respiratory diseases. These macrolide complexes obtained will then be used to perform wet lab studies to determine their efficacy and activity. Overall, this has been an exciting journey with a lot of learning. I would like to thank my biology teacher, Jenna Ronan, and my mentor, Errol Bakabasi, and advisor, Dr. Avinash Mehta, for all their guidance and support. I look forward to the feedback and continue to work on this project.